Coral, ICRA, RSS, as well as IROS. He led the perception as part of Team MIT Princeton in the Amazon Robotics Challenge in 2016 2017. And he is also a recipient of the Princeton SCAS Award for Excellence, Japan Foundation Paper Award, NVIDIA Fellowship 18, and Gordon Y.S. Wu Fellowship in Engineering and Wu Prize. His work has been featured in the press, including the New York Times, BBC, and Wired. Andy, take it away.
Thanks for the intro, Albert. Is my screen showing okay for folks? Okay, cool. Well, excited to be here, and thanks everybody for the invite. And I'm glad that I get to spend some time to talk to you guys about things like the things that we're doing at Robotics, and yeah, I really appreciate it. So I know that a couple folks were really interested in hearing more about Codex policies, and I figured I would lead up to that, but ultimately wanted to give some context for how we got to this point in some of the background and various directions that we were thinking about before we ended up at Codex policy. So hopefully that could also help inform the longer term trajectory that we're shooting for. Cool. So what I'm really excited for in the future when I think about it is one where robots are around us, helping us with everyday tasks. And I think that part of that story involves robots that are moving around and manipulating objects in the world and being able to react to unstructured feedback and having humans be able to work alongside and teach these robots. And personally, for me, I think it's also in the pursuit of generally intelligent machines. It's an opportunity for us to build decision-making agents that interact with the world and improve themselves over time. So depending on if you're also interested and excited about things like AGI, I think that robotics is a fantastic benchmark to kind of test that out and see if AGI truly does work. Because in the real world, that's when rubber meets the road. And for a long period of time, I've been working in manipulation with machine learning, getting robots to pick stuff up, put them down, toss them around. And I think one of the things that I got really excited about was, in particular, seeing the transition from non-data-driven methods into more data-driven methods. And when I was still a grad student at Princeton, I had visited Alberto Rodriguez's lab a couple times, and there was a lot of discussion about how pushing is a really subtle, seemingly simple task, but it's actually, there's a lot of complexity that's baked into it. So if you have an object, for example, and as you're pushing the object is going to, for example, slip away from the fingers, and your model has to be able to use some version of closed loop feedback to constantly readjust the trajectory of the object. And that's where all of the subtle challenges lie, because in doing that, you kind of also need to have an implicit understanding of the dynamics of how the friction of the object reacts to the friction of the table. But then it was just really exciting to see that machine learning could kind of make that all of those subtleties sort of go away with enough data. So implicit behavior cloning, I'm still surprised by some of these demos that we had ended up doing, which was like sorting objects and having the robot learn how to push objects and sort them around. And this is all closed loop vision-based policies. So the only input to the input is the RGB image, and the output is like end effector offsets. So ultimately, I think that through manipulation, I think what I'm really excited for is a direction where we're interacting with the physical world to learn some notion of shared bottom-up common sense. And the idea is that if we learn over enough tasks, then there will be some shared priors of learning how the world works. And ultimately, that could take over in terms of asymptotic data collection. So specifically, in 2021, we got really excited with scaling up an arm farm, which we called the Mars Reach Arm Farm. And during this time, we had started setting up a bunch of various different tabletop tasks, like pushing objects around, pick and place, folding t-shirts, and various different levels of complexity. And the hope was that as we collect more and more data over the tasks, then ideally the total amount of data that we needed to collect to learn every new task would asymptote over time. With the idea being that at some point the shared priors would take over inside of the neural nets that we were training. So we would collect data with teleop and then hope that the amount of teleop data we need to collect over time would be less and less. But the reality of the situation was that the curve was much more linear than we expected. And this is particularly because there's so much complexity that's just packed into the environment, the embodiment that you have, the contact physics, various things like different action spaces, all of those things sort of mashed together into that bottom axis there, which really makes it the kind of data that you observe incredibly diverse. And this is part of why I think that we will still see a curve in the long run, a logarithmic curve, but then I think that this is probably much more far out, and we're only sort of scratching the surface in terms of if we have a setup like the one that we had. So at the end of the day, we learned some harsh lessons, and I think one important one is that at the end of the day, machine learning is a box. It's very good at modeling the data points inside the box, but not very good outside. So you can imagine that if you have a lot of training data points that are that you've modeled with your neural net, then so I can't tell you how many times we've created this sort of plot where if you took all of your testing cases and then you plot them on some manifold or latent space, and then you visualize the test cases that you perform well, they would almost always lie within the convex hull of your training data. So the blue ones here are the ones where the test cases perform well, and the red ones are the test cases that don't. And then this gray line here is our convex hull of our training data points. And we've created this plot multiple times for various different projects, and it's always a similar case, which is that you can only model what you have training data for. And every time we get stuck, it's one of those things where you want to get inspiration from other fields. And I think that in robotics, we care a lot about generalization and extrapolation, and there's certainly ways in which you can also encourage that more implicitly through the architecture design of the model, or maybe through training data regimes. But ultimately, when we look at another field like NLP, you'll realize that they've decided that it's a good idea to stick your whole universe inside the box so that every extrapolation problem becomes an interpolation one. And this is, I think, has manifested itself best in the form of large language models. There's a question. Are these plots affected if there's compositional structure in the data when doing extrapolation? Yes. So in some sense, I think that if you carefully control for in your training data how much of the compositional generalization or different attributes for which you can, upon linearly extrapolating, be able to get a successful extrapolation data point. Okay, I think maybe a little bit of a detour, but neural nets have an eigenbias, which is that, and you can see this when you're modeling, for example, some particular output function. You're trying to train a model to take an X as input and predict Y. And these neural nets, oftentimes they can interpolate between those points because there's this eigenbias that drives the model's ability to basically interpolate between these two data points. If you carefully control for settings, and this bias happens most frequently for MLPs and less so for transformers, but specifically for MLPs. So if you are trying to generalize along some known axis that is a linear type extrapolation, you can actually control your data in a way such that you can get the extrapolation for free. This is something that we did poke at in the implicit behavior cloning papers, so I would check there for more details. Because there was also this bias where, depending on the structure of the problem, you can tweak it in a way where it can get the right kinds of generalization that you expect. For example, if your task was like constantly pushing the end effector from one position to another and it was making a line, then if you kind of let the policy keep going, it might just continue doing the same thing. So there's maybe we can also bring that discussion offline as well.
No worries, thank you.
Yeah. So large language models, I think they're absolutely fascinating because it's one of those things where as long as the model is big enough and you stick all the different kinds of data sources in, they just happen to, the model exhibits impressive compositional capabilities. And this is one of the things where you can take your favorite off-the-shelf language model and type in things like steps to brush teeth with peanut butter in the style of Shakespeare. So it's combining concepts it's acquired from 2 different data sources. And then it generates, take a spoonful of peanut butter, spit it o'er thy toothbrush, and then ending there with smile wide and admire thy pearly whites. And I feel like after seeing some of these results earlier this year, it's one of those things where it makes me question the meaning of creativity. Anyways, the language models, ChatGPT, folks are probably familiar. I think the thing that's really powering these models, there's 2 aspects. One is the tokenization, and then the other aspect is transformers. So in the tokenization part, we have byte pair encodings, and you can think of these as pieces of words. So how it's done is that you would take characters, for example, and then you would cluster the characters together based on how frequently they appear next to each other. Tokenization in NLP has traditionally happened per word, and that still gets us the best performance if you were going to use that in language models. However, the reason why BPE encoding is better is just because you can express more with less tokens. So you can imagine that previously you need 6 tokens to express these words, whereas if you break it down, then you can express the same 6 words with only 4 tokens. There's some efficiency gains there because then your vocabulary may not have to be as large. For transformers, which is the modeling side, I'm sure folks already see this diagram many times, but the thing that I wanted to guide your attention to is the self-attention mechanism. So each time that you compute a feature vector output y, and that is a weighted sum of the feature vectors that are coming in from all the other tokens, x1, x2, and x3. The interesting part is that the amount of contribution in terms of the feature embedding coming in from x1 and that contribution going into y is weighted by the distance between x1 and y. And this is, there's an important distinction here because the metric space upon which this distance is computed is on a metric space that is separate from the actual payload embedding that x1 carries. So you can think of the query and keys working together to construct your metric space. And then your values are actually the payloads that are on top of each feature embedding. So this is particularly important because now you can start thinking of several other kinds of architectural design choices as being a subset of what you can model with self-attention. For example, if the metric space was instead just based on spatial locality, then you get something that looks an awful lot like convolution. So I think this is really an amazing piece of architecture. And I think just the biggest difference to a lot of things back then is that how much x1 contributes to y, and based on that metric space, but that metric space was always like something like L2 distance or L1 distance to x1, which didn't quite have the same level of expression that some of this architecture has. So the idea is that if you take self-attention and then you layered it multiple times and you get a really big model, bigger is better. So one of my favorite examples of this comes from a talk from Noam Shazir at WeCNLP. And the task was you would train a language model here with 33 million parameters on all of Wikipedia, except for the article on Abraham Lincoln. And the idea was that in order, at test time, you would ask the model to predict Abraham Lincoln, but that it would need to piece together information that it has learned about Abraham Lincoln from all the other articles it has read. So you can think of this as strictly a task of interpolation because it's compositionally trying to piece together something that is still in distribution of the training data. So if you have 33 million parameters, the article that it generates is absolutely bogus. It doesn't make any sense. Abraham Lincoln was an American voodoo activist and a former alcoholic. But then when you scale it up to 97 million parameters, then it starts getting some of the punctuation correct, a little bit of the grammar correct as well, but none of the facts are correct still. 320 million parameters, you can see that the formatting starts to look better. Some of the sentences are also more coherent, but then still the facts are not correct. It's only until you get to 1.1 billion parameters that the model starts to be able to successfully construct something that looks like it was written by a middle school student. And then once you get to 5 billion parameters, then you get a nice, really nice and clean article of Abraham Lincoln. And keep in mind that the amount of training data here has been fixed the whole time. The only thing that's changing is the size of the model. So I think this was really cool to see. So for us and over the past year or so, I think that a hypothesis has been that if we took language models trained on internet scale data, then somewhere in the space of interpolation lives to some degree things that can help us with robot planning, visual common sense, and robot programming. So a simple example of this is take your favorite off-the-shelf language model and type in something like steps for a mobile robot to fetch a Coke can from the refrigerator in the kitchen. And then it would give you a semblance of a plan, locate the refrigerator in the kitchen, use sensors to detect the presence of the Coke can and move the robot towards the refrigerator, etc. And now really the only thing left to do is to ground each of these steps into for example, APIs that you have access to on your robot or low-level policies that you've trained. And this is where Socratic models and PaLM-Se can come in, where it was a proposal to try using these models to build robot systems where language serves as a form of middleware. And a simple way to do this is you can take a visual language model and have it be able to detect objects in the scene and give you a scene description of what's inside the scene. Give the human input, which is the task, move all the blocks to different corners, and then you pass it to large language models for planning to give you step-by-step plans. And then for each step in the plan, you can then pass it to language condition policies. So this could be, for example, clipport, which is clip conditioned transporter nets, and that could allow you to do various pick and place tasks. So if you end up doing this, we have some code online that you can play around with, and this is a live demo of what that looks like. It's you can move all the blocks to different corners counterclockwise. The robot would do the thing, and then during when it's the language model will be called to generate step-by-step plans. And then for each step in the plan, it's going to generate a picking and a placing heat map, and then sort of just execute each step at a time. This particular implementation doesn't have closed loop feedback. And so a follow-up to this particular framework, you'll notice that the visual language model only appears once at the beginning. You can technically interleave the visual language model all throughout the planning process so that it's also doing replanning based on feedback and success detection. So you can do that with inner monologue, which is effectively taking things like existing success detectors to help us determine if a task was completed and then replan accordingly. Okay, so we were really excited to see what language could do for us, but then there's also lots of different limitations. Language itself as an information bottleneck, there's lots of caveats to it. One is that it loses spatial numerical precision. Two is that it's highly distributionally multimodal, so there's lots of different ways to say the same thing. And it's also not as information rich as other modalities. So you can imagine if you wanted to pass in images, there's a lot more information that can go in there. And also another sort of thought that we had after this was, is it that language models can only serve as high-level planning type things? So we have Socratic models and inner monologue for perception type problems, PaLM-Se can, and Wenlan et al. For planning. For control, is it the case that we always have to continue to stick with imitation or RL or engineered policies? So one thing that is clear to us at the time, at least, was that intuition and common sense, which we often get from language models, it's not just a high-level thing. Like it's something that applies to low-level behaviors too. So for example, if you're going to tell a robot spatially, move a little bit to the left, what does a little bit mean? I think that's very much contextual. And there's a little bit of common sense that's baked into that. There's also temporal, move faster, or functional, balance yourself. We think of these as modes of behavioral common sense, and we can think, I like to think of it as the dark matter of robotics because we know that it should exist, but it's really hard to pin down. So the premise here was, can we potentially extract some of these priors from language models? So this is how we landed at a sort of early experiments last year. Jackie was interning with us, and we ended up getting some interesting signs of life in terms of getting the prompting language models to be able to write robot code. And through this process was also able to get it to express some notion of behavioral common sense. So for example, if you just go into your favorite language model, we can do things like if you see an orange, move backwards. And then we can like type in if detect object orange robot dot set velocity x is equal to negative 0.1, y is equal to 0, z is equal to 0. And here we're effectively typing in our instruction and comments and then giving the language model an opportunity to figure out what are APIs that we're working with. And so the idea is to get the model to compositionally generalize on this. And we can say a new command. So move left until you see the apple. And we can get the language model to generate the output here. There's a lot of things going on in just this simple example. The first one is that it's switching the objects accordingly to the new command you've given. Another one too is that it's changing the if statement into a while statement depending on what's being semantically parsed. And also it's assigning a canonical coordinate frame. And all of these things are kind of given to us for free. We can also say things like do it again, but faster to the right and with a banana. And it's going to, for example, speed it up just a little bit, but then also flipped the axis there so that it can go to the right. So this sort of natural assignment of the canonical coordinate frame, and then also like semantically parsing things like faster accordingly is really nice signs of life in terms of behavioral common sense. And then we can also say, tell me why you stopped moving. I stopped moving because I detected a banana. Great. So that's a little bit of a demo of the kinds of things that Codex policies can do. And this is powered by two things, I would say. The first one is that when we often write code, so language models are trained on, at least for the code writing ones, they're trained on a lot of GitHub code. And the way that people write code often follows this chain of thought where you type in comments for the feature or the functionality that you hope to achieve in the code snippet that follows after. So what this is doing is a little bit of scaffolding the robotics problem inside of that framework so that it works nicely or into that format so that it kind of follows that more naturally. It's kind of in distribution of its training data, except that it's doing it for robot APIs. The other thing that makes this possible is that, and I'll come back to this in a bit, is that language models are trained for in-context learning. So what is in-context learning? One of the biggest differences in the GPT-2 and GPT-3 models is that when you're training on your data set, you're pulling examples from the same task, from the same data set, and packing them together in context buffer, and then having the model auto-regressively predict subsequent things so that doing the new task for the new example becomes just predicting the next thing. So it's trained with autoregressive models with packing. So those who are familiar with seek.io, packing is doing exactly this. You have this is a translation problem here from Maison House, French to English. And ultimately, the examples in the prompt tell the model what distribution of task it's going to be doing. And the completion just follows along accordingly. So here, you can have X, Y, X, Y examples and X query predict Y. where your function f is drawn IID from your distribution of functions that you're trying to train the model to be good at meta learning during training time. And there's lots of folks trying to better understand how the generalization works. But there's some interesting properties that people are observing, which is that transformers at certain scale, they can generalize to unseen F, unseen tasks. And they can do this somewhat better than MLPs. And also they tend to work better with non-recurrent better than non-recurrent autoregressive sequence models. So if you want to see in-context learning emerge naturally from training on data, you would see it happen more often with transformers than you would see it with RNNs or LSTMs. So this is in-context learning in general because you're training on the order of tasks. This is a mode of supervised meta-learning. And historically, how this came to be in NLP is that previously, in order to train a multitask model, so there were sort of three versions that popped up. The first version was just you have input, output, and then you would train this input-output type model on many, many tasks. But that was tough because you had, for example, say that if you had a multitask model trained for a captioning task, and your output was going to be captions, textual captions, then the length of the captions would very much bias your evaluation metrics, because say that you had dataset A, which had short captions, and dataset B, which had long captions, and you mix all the training data together. If you just have an input-output model, the model's going to be confused on when it should be predicting a short caption versus when it should be predicting a long caption. And so that would mess with your NLP metrics, especially for multitask, because it's like it would predict a short caption when you're on the testing set for a long caption, and then your blue score would just be terrible. But then what kind of helped in this was that you start feeding in task IDs. So these task IDs would be specific to the data set that you're training on, and that would inform the model what distribution of caption length that you needed to be conditioning on. So that's the second version. And then the third version was realizing that instead of task IDs, we're going to feed in actual examples of pulled from the same data set. So these actual examples will help define the distribution on which our new prediction of this query should be conditioned on. So you can imagine your prediction of f of x query here is conditioned on both x query and a distribution that is defined by your examples that you've packed in context. So this is incredibly powerful. And I think I'm happy to also talk offline about there's like various different ways in which you can play around and control this distribution to make it do depending on how you've in context trained it, you can get test time behaviors that are even more powerful than what we've observed happening with just random sampling. But yeah, there's lots of interesting things there. So in the Codex policies paper, it's driven by the way we format code and also in context learning. So in that case, you can pass in examples of robot code and then have the language model piece them together in new ways in order to do new tasks. And one particular, this harkens back to work from classic work in robot programming, which is generalization through modularity, infinite use of finite means. And here we have, for example, perception and control APIs that are fixed. And whenever there's a function that is being created or hallucinated by the language model that's undefined, then we have a particular approach where we call it hierarchical code gen, but really you can think of it as recursively generating code. So if it finds a function that's not defined, then it's going to try to define it. And so that's what this is showing here. So this ends up working really well in our robotics benchmarks. But I think that if you go into the paper and go into the appendix, you'll find results that show that were also state of the art, at least at that time, for NLP benchmarks too. So we had hierarchical codegen and hierarchical prompts with our P at 1 score. This at the time was state of the art for NLP codegen. And so I think this is a powerful tool. You can have these language models dynamically generate a code base and expand it over time until it's actually runnable. And then there's a fair bit of expression that could be gotten from that. Another thing too that was showing up in the Codex policies paper but didn't make it to the main paper was in the appendix is modes of generalization. And I think one really cool thing about being able to do these experiments in terms of generating code snippets is that you can also measure attributes of generalization that these code snippets are measuring. So I think this is maybe less of a specific point on Codex policies, but more about how we should be measuring generalization in robotics in general. There's a paper by Dukub Keys et al., compositionally decomposed, how do neural networks generalize? If you go down to this figure here, figure 1, they were studying this in the context of grammars and language models, but there's something, I love this split in terms of modes of generalization. You have systematicity, which is how well you can recombine known parts. So this is like you have 2 examples here, and then you can recombine parts of the 2 examples. So each row is an example here. You can have productivity, which is chaining together multiple examples to handle longer examples. You can also have substitutivity, which is replacing modules. You have localism, which is an understanding of hierarchy when you're replacing different parts inside of your examples. And you have overgeneralization, which is that really defining what that boundary of generalization looks like. And these are 5 axes for which you can measure generalization in for language models, but I think it also applies for robotics in general. You can think of it like whether it's like piecing together motion primitives for new tasks or like changing your environment in meaningful ways. I think all of these properties can still apply to whichever way in which you want to measure generalization. So I feel like this was very much underlooked in the work. I feel like it would be great if more folks in the community also measure generalization with these 5 axes, because I think it's quite, I think is really interesting when you, for example, see a model being really good at something like systematicity and productivity, but finding that substitutivity sort of struggles, then I think that that gives us some more signal on which parts of the model architecture we need to be tweaking, or how we can better handle our training data distributions.
Sorry, what's overgeneralization here? What does that mean?
Yeah, so here in overgeneralization, it's like sometimes if, for example, we have an overarching rule that is, or an overarching grammar that encompasses multiple data points, if we have an exception to that rule, how quickly can the model adapt to that exception? So it's a bit of a like kind of a bit more less of like a capability, but more of just like measuring where that fall off happens. So there are ways in which that could be measured explicitly for, but in an environment, it would be like if the robot is always going to be sitting in a chair, but then it happens to see a chair that you can't sit on, and you want the robot to adapt to that as quickly as possible. How do you measure that?
Got it. Thank you.
Yeah.
All right, we have a question in the room as well.
Yeah.
So what's your hunch about what are the hardest types of generalization from the ones that you talked about?
Yeah, I think one of the hardest ones, at least that we've seen in classically in robotics, has always been systematicity. And I think that one is still the one that people always think of when they think of compositional generalization, which is you have, say that you've learned a path from A to C, which is A to B to C. And then, or just like being able to piece together subparts of paths that you've seen before in order to construct a new path. I think that that has been the dream for things like offline RL. but I think we haven't really quite seen it happen in offline RL. So I think that that is probably, at least in my opinion, one of the more challenging axes of generalization to really nail.
I have a follow-up question on that. So when we say systematicity, right, like we can't expect this kind of composition generalization in all modalities. I think it makes more sense when, let's say, we have NLP or textual tasks as compared to like just visually navigating through the system. So is there a notion of which kind of systematicity is more easy or is more intuitive?
Mm-hmm. Yeah, I don't have a good intuition, like at least across all modalities and across all task distributions, what kinds of areas in which systematicity would be more useful. And so in some sense, I feel like we need help from the community to really apply some of these measurements in the first place to those modalities. And also, for example, in the case of, visual tasks, how do we measure systematicity in the first place, I think is still also relatively less clear to me. So I think, if there's ways in which we can formalize it and maybe also just begin using it as a metric that we keep track of when we're doing evaluations, I think that we would have better idea over time.
Yeah, I think the important thing is it does make sense for language tasks, like more so in language and text as opposed to like visual tasks. So I wonder, like, to what extent this, and I think it doesn't matter if we don't have the exact number or anything, but I feel this has not been explored at this point for the large language models, right? Like they are doing a lot of wonderful things, but nobody has really looked into to what extent they are doing this, right? And that's what you're saying, we need help from the community to kind of do that as well.
That's right. Yeah, we need help from the community on the large language modeling side. I also think in terms of whether or not this applies for vision tasks, one example is VQA tasks where conditioned on the right kinds of questions, if you've trained on a data set that has lots of descriptions of cars and another data set with lots of descriptions of human activities, then ideally there's a compositional generalization where now you can answer questions about human activities next to cars.
Right.
And so I think in the vision domain, it also applies, but it's just a question of whether or not that's something that we can actively measure and figure out where are the spots in which it struggles.
Right. I do have a small side question. I also posted that in the chat, but we do a lot of in-context learning where we do this kind of chain of thought prompting, where we kind of let the model tell that it needs to reason in order to complete the task. Has this been tested that, let's say, we systematically change that prompt? Like, let's say if I tell it 2 plus 1 is 3, and I say, okay, 2 plus 1 is 4, like I always add 1 to the output. Does the output from the model change as well in a similar fashion, or it can still produce the right result? Like, do you know if this has been explored yet?
Yeah, I don't know about the specific problem setting of like always adding 1.
Yeah, just an example. Yeah.
Yeah, one. But overall, I think one thing that in-context learning helps a lot with has mostly been in terms of formatting. And the formatting is helpful for maximizing blue score metrics. So if you want to do well on all the data sets, then learning the format first and foremost really helps with that. I think in terms of more implicit rules that are overarching inside the in-context examples, like that the numbers are always off by 1, I think that kind of in-context prompting would benefit a lot from some mode of additional training on data that looks like that. So specifically, if you had lots of examples where the in-context examples were always off by X, where X is some random offset that you've chosen, but is consistent between the examples, then you can expect the model to generalize to that. So I think that the challenge with working with existing language models is still from the fact that we sometimes don't know exactly, on our side too, like not knowing exactly what their training distributions are. And so if we wanted to compensate for a new capability, then ideally we fine tune the models on a similar distribution of function f.
Yeah, I was just like a side thing. I was also thinking this to be a way to test what the models are actually learning. It seems like they're learning the right thing, but if they're actually learning the right thing, then they should be also robust to like those weird noises that we introduce in the in-context learning. So it can go either way, right?
Yeah. In some ways, that particular test is similar to overgeneralization. So it's like an exception to all the rules that you've learned in your training data. How well can the model adapt to that?
Yeah. Okay, thank you.
Cool. All right. Cool. So jumping on, we have videos of Codex policies doing a variety of spatial tasks. What I love about having it write Python code is that you can use all the pip packages, and language models are fairly familiar with them too, albeit maybe outdated APIs, but using NumPy and SciPy to draw convex holes and do various different spatial reasoning tasks is pretty cool. We have this example on the bottom right where the model is prompted to draw a pyramid under the sun. It's pretty cool. Another thing that appeared in the appendix didn't show up in the main paper, but if we go down to this example here, this is one of my favorite side examples. In robotics, and when we think about a model that can do it all, for all robots, a key question is like action space. So how do you have a model that can handle multiple different action spaces? And I think code is an interesting possible example of being able to generalize to new action spaces if the action spaces was just different APIs. So here we have an example of prompting the model with omnidirectional robot. Your available actions are move up, move right, and move back. And the task was to make a U shape 5 meters wide and 10 meters long. And then it would just do the thing. But then here we given an example, additional example, unidirectional robot, available actions, turn left and move forward. And then we asked the model to predict what the plan should be for moving a U shape 3 meters wide and 8 meters long. And then it's kind of cool to see that the model can just, based on the description of the APIs that are also kind of linguistic by nature, being able to chain together a plan that looks correct. And I think there's some opportunity here to think more about, as we approach systems that can work on multiple different robots, what would a shared action space look like? Maybe it's code, I don't know. Cool. Let's see. Yeah, these models are multilingual as well, especially if they're pre-trained on multilingual data sets. So you can talk to the robots with emojis. We also have a couple extensions to Codex policies. So one of which is visual language maps. And the main approach is that as a robot is navigating around, you can fuse all of your vision language features like clip features into a voxel grid or a height map, for example. And then that allows you to generate heat maps for locations of interest that you can query with natural language. So the area of the sofa, the area of the chair gives you a bunch of hotspots. And then if those are just coordinates, then you can use Codex policies to parse in natural language commands and then basically give you new locations that you can travel to. So for example, if you wanted to say things like move a bit to the left of the sofa or in between the sofa and the chair, then there's an opportunity to do that. Yeah, Glenn?
Yeah, so I was thinking a bit more about some of the examples. I'm wondering if you've got any input or like information on like when the system generates, I'll call it a non-optimal program, but one that's still successful. So do you have like some tips there? Does it generate non-optimal programs for control policies, and what would you do to improve them?
Yeah, it's a great question. Non-optimal policies happen quite frequently, especially if the task is very long horizon and the robot, at least in the initial planning phase, doesn't have access to all the information of the environment. I think that one way in which that could be resolved is one, doing some version of replanning every time that it's like incrementally making progress in that particular policy. So as opposed to doing the thing like we did in Codex policy, which is execute everything open loop, instead execute it halfway and then like reevaluate based on current conditions whether or not we should make changes to the code or the plan. The other side of things too is that if we can recognize or have some version of language feedback that describes exactly how it was suboptimal, then we can feedback that back to the language model as a mode of reflection to get it to truncate the code, and then maybe pass that to a data set that we can refer to later for in context prompting future examples, or maybe even training the fine-tuning the language models to be better.
Mm-hmm. Just one quick question about the first example or like option. I guess, have you thought about looking into, or like an example for generating code and it'll add checks, like, you know, go forward however far, and then it'll start to learn, okay, stop, take a picture of the environment, see whether or not things are still valid. So like incorporating that into the first version.
Yeah, absolutely. I think that if it's doing checks and calling perception APIs, those checks can be assert statements. There was the prog prompt paper that also came out roughly the same time. And one of the main emphasis of their work was using the assert statements as a way to do the code checks. And I'm gonna see if we can find one of their examples.
Okay.
Yeah, I think definitely there's like lots of logic structures, and depending on which language you're using, various different things that we could potentially exploit to get it to work. So I think here they're like example tasks: assert close to garbage can, else find garbage can, which is a really neat way to formulate it too.
Okay, thank you.
Another extension to Codex policies has been getting the language model to write cost functions or reward functions. And then you can optimize these trajectories with MPC or RL. And I'm particularly excited about this because it's doing like really interesting reward engineering that would have taken a lot of time for humans to come up with. And as long as you have sufficient examples of easier things, then it could recompose the APIs in meaningful ways to do new things. So some of the things that we've shown are like getting the robot to twirl around or do a moonwalk, and also a couple of manipulation examples too. So I have more slides that are talking more about big picture stuff, but I figured in the last 8 minutes, I'm also happy just to get into discussion mode and talk more about various different things either related to Codex policies or not. Oh, there's a question from Charlie. These are cool results. Do you have some insights on how to scale this to tasks where we don't have good code for example, locomotion tasks, agile, robotic stuff, etc.? Stuff where we use small MLPs to learn control policies instead of coding them up. Do you envision LLMs that code up PPO training scripts or something different? I think I'm really bullish on getting reward code to be the platform for which we could potentially specify more complex trajectories. In particular, because MPC is just so powerful, it also drives much of the mobile manipulation tasks that Boston Dynamics has been doing. And you just can't get that kind of full body manipulation without MPC. So I think, like, in my opinion, at least, I feel like getting a language model to semantically parse context and instructions and then bringing it down into a form that is digestible by MPC could be a really promising direction for that.
Something I've been curious about, and you mentioned it a bunch in your talk, is that now the discussion of like what is out of distribution for models that are trained at this scale has to be more nuanced, because it's not as clear exactly like what is in distribution and what is out of distribution. And so we need to better formalize that. And I'm just curious, like, what are your big picture thoughts on that? If you know any cool papers that shaped your thinking here. That's something I've been thinking about a lot over the last month.
Yeah. One thing that we've realized on our side too is, let me actually pull that paper up real quick. So this is a work on general pattern machines, and part of the paper was looking at if we, well, first of all, context, the language model is being used here to decipher various different sequential patterns, and some of these patterns are like benchmarks that folks had thought were really hard for general intelligence for a long time. One of the benchmarks that we started testing on was, we called it the PCFG benchmark, which is probabilistic context-free grammars. This is a synthetic benchmark that just has arbitrary sequences of tokens that are chained together. And you have multiple in-context examples of this. And the expectation is that, say you had some function that was defining your particular sequence of tokens. So imagine that you had a sequence S1, S2, S3, and then this is followed by the swapped tokens here and removing the second token. There's a feature transformation that defines your input to output example. And the idea is that if you feed in multiple input output examples without feeding in the function rule, then the model, if it's good enough at in-context learning, it can do continue like generalizing this particular function, applying the transformation to new examples. So why this is relevant is that you can, because this is a synthetic benchmark, you can actually synthetically measure, as you increase the number of functions used to express these transformations, the more complex these patterns become, and at some point they start to look really random. And like with this increase in quote unquote difficulty of number of functions used to express the rule, that also tends to be more and more out of distribution of what the language models were trained on. So you can think of it as kind of like a metric on which we're measuring, okay, how far away from the original distribution can we get? And what we realized over time through these experiments is that at the end of the day, these transformers are they're universal function approximators, and what is considered hard for the model is just what is out of distribution. And what is out of distribution is just things that maybe can be synthetically generated and become more and more random. But ultimately what this benchmark gave us was just a good sense of like where that fall off starts to happen. So I think that is one way to measure it, but there could be other ways too.
That's really cool. Thank you. What's the name of the paper?
Yeah, this one's called Large Language Models as General Pattern Machines.
Okay, cool. Thank you.
Yeah, has this been tested in terms of inheriting these functions?
We also have a instruction-tuned version of these experiments where indeed it's passing in examples of functions and then also example inputs and outputs. If you do condition on the functions itself, the generalization, it does it pretty well, but then you still get the fall off where even more complex functions, it starts to break down. And that happens at a much later level. So for example, if we start performing, usually starts performing fairly poorly when the number of functions exceeds 20. But then if you have an instruction to model, maybe 20, it can still work okay. It's just that when it gets to 30, then it starts to struggle. So yeah, you can kind of see these nuances for when it starts to break down, depending on the way that the language model was trained too.
So here, I think the order in which you apply these functions is important, because there might be multiple ways to do something, right? It doesn't have to be a sequence of a specific set of functions, but maybe it has found ways to get the same output using some other order. So how is that evaluated?
I think that we didn't quite measure the redundancy of functions themselves, but I think that would be really interesting to look at. I think that here we were just mostly measuring the per token accuracy of the example outputs that were being predicted.
Oh.
Yeah, but yeah, it could be really cool to see exactly how well it handles similar functions or functions that do the same thing but look different.
Right. Okay.
Yeah.
I had a quick question. So I was curious if you saw any like more common problems in LLMs in the Codex policies, like for example, hallucinations or nonsensical policies. Like what kind of nonsensical code would it write in terms of?
Yeah. We see that quite often, and when it doesn't work in terms, especially when it gets into like when you start using pip packages where the language model has been trained on really outdated code, then that becomes an issue. Or, for example, you ask it to do something and it hallucinates a particular chunk of code that doesn't quite seem to make sense, or maybe is like using some syntax that cannot compile in Python, which is a common problem too. I think one particular thing that's been really interesting for us as well is figuring out how to quantify uncertainty before it actually makes the prediction. So in Robots Ask, this was a project that Alan had led. Here in this project, they were using we're using language models and conformal prediction to. I'm getting kicked out of my room. Sorry.
Thank you. Yeah. Here we go.
So here we use conformal prediction to whenever we're making a prediction of the next token, you can take the probabilities of that token, and if it exceeds a threshold, for example, then it's confident. But if it's not, then it's not confident. And whenever you can use that as a signal for downstream asking additional questions, or maybe also additional processes that can basically say, okay, we're going to pause on generating this plan. Let's have a human intervention or something like that. How this threshold gets generated needs to be statistically relevant. So you can do this with conformal prediction. So in the paper, if you go into the details there, conformal prediction, or actually, maybe we have a figure of that here. Yeah. So conformal prediction, the way it works is that you take 100 examples of previously good generated code, and then you have, for example, uncertainty bounds that you want to quantify on that small data set. You can use that as a way to determine what that threshold would be at test time. So I'd recommend going into that and checking out how we've done it there.
It's great. Thank you so much for the talk. And seems we're running out of time, and you also got kicked out of your room. So yeah, thank you so much, Andy, for the talk today. If anyone has follow-up questions, where should they reach you?
Feel free to send me an email.
Oh yeah, perfect. Yeah, and there's also like a video will be uploaded to YouTube as well. So yeah, thank you so much for the talk again. I've been a personal big fan since the Tossing Bot days, and then Viral also mentioned you're one of the world leading experts in robotics. So really great to have you here. And yeah.
Appreciate it. Thanks for having me, and thank you all for your time.
Thanks again. Take care.